there is a slightly, in 3D, this happens in 3D, we're only looking at it in 2D. So let's look at it in 3D and see what this looks like. Okay, here's our charge. We're going to give it a kick down. It's going to radiate. This VPython program shows you the electric and magnetic fields in the pulse spreading out in 3D. So here's the charge. That was its acceleration. We accelerated it briefly. And in 3D, we get these electric and this pulse of electric and magnetic fields spreading out from the charge. Let's run it again. And so we're going to accelerate it. Come on, we are going, there we go. And we see that it's the radiation spreading out in a 3D pattern, E perpendicular to B, and it's just going past us. We better back up a little bit. And it keeps spreading out and spreading out. It does fall off with distance. So as it gets farther and farther away, the magnitude of the fields decreases. But in fact, interestingly enough, the distance dependence is only a 1 over distance dependence. So it's a 1 over r distance dependence, not a 1 over r squared distance dependence. And so electromagnetic radiation always wins. If a charge gets accelerated and radiates, the pulse of radiation only falls off like 1 over distance, whereas the static field falls off like 1 over distance squared. So the radiation is what you're going to notice the most if you're at any distance away. And notice one other thing about this. Let's run it one more time. Notice one other thing about this. Notice that the radiation is strongest in directions perpendicular to the acceleration, and there's actually nothing at all right along the line. So if you're right along the line, you're not going to detect this radiation, whereas if you're perpendicular, you see a lot.